Welcome to the Control Engineering webcast, Empowering Machine Builders for Virtual Factory Acceptance Tests, sponsored by Siemens. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having technical problems with the audio or slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speakers in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded and you will receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. I'm happy to introduce today's distinguished speakers. Scott Felber is an NX Product Engineering Software Marketing Manager with Siemens Digital Industry Software. Scott's main task is to help customers and prospects identify value around use of Siemens software products with the main focus on NX for design and how that integrates into their processes. He also can discuss use of NX in the context of Team Center, process automation, and many other upstream and downstream uses for the design data. He works with customers and prospects to help them build a plan to transform their businesses and processes by identifying non-value activities and ways to eliminate them. Before joining product marketing, Scott spent over 15 years in pre-sales with a primary focus of selling to industrial machinery companies. He has over 25 years with Siemens Digital Industry Software and holds a Master of Science in Engineering Management from Marquette University and a Bachelor of Science in Industrial Engineering from the University of Wisconsin-Milwaukee. Colm Gavin has worked for Siemens for 19 years and is currently responsible for the promotion of digitalization topics from Siemens Digital Industry Software Group for machine and line builders. In this position, he has leveraged his experience in discrete manufacturing to help companies take advantage of the new innovations coming with Industry 4.0. Prior to this role, Colm was responsible for the marketing of Siemens' totally integrated automation portal software in the U.S. and also worked on the development team of this software in Nuremberg, Germany, focusing mainly on the usability and design aspects of engineering software. Colm holds a bachelor's degree in manufacturing engineering from Trinity College in Dublin, Ireland. Colm, please go ahead.
When we look at the requirements for the manufacturers, we said reducing the startup time inside the facility is absolutely key. So the early validation of the machine sequencing and throughput, how can a machine builder or line builder show that to an end customer that what the machine that they're building and that they're supplying is actually going to meet the demand? Then we have the easy error handling and fault recovery. Again, all part of reducing the startup time for the operators. How quickly can they get the machine up and running? Manufacturers will want some validation of that. And of course, the cost for actually traveling to do an actual factory acceptance test, we want to maybe reduce those, because if we're going to do design reviews in the early stage between manufacturers and their machine builders, if we can do that virtually, that's going to save a lot of time. And especially now where we have reduced travel, or in some cases no travel now, whatever we can do to do these virtual factory acceptance tests is going to be key. They want flexible handling. How can I run different products on one machine? It depends on the level of machine sophistication to be able to run the different parts. But if we can simulate that or show that, or if I have retrofits, on the machines? How can that be proven to the end user that the machine can handle it without major downtime or disruption? As we mentioned earlier, the quality parts are absolutely key, goes without saying, and being able to do predictive maintenance to assure smooth operation. But of course, many of the end users and manufacturers we talk to, they talk about the training, being able to train an operator where there might be some high turnover rate, or even before the machine shows up. How can you train an operator to use the machine and operate the machine easily? So all of these requirements, reducing the startup time for the machine coming into the facility, flexible product handling, quality parts, and operator training, they're just some of the many requirements we see manufacturers looking to simulate or do as much of this testing as early as possible and in a virtual manner. So we're using the terminology virtual factory acceptance test. It could be virtual machine build, whatever terminology you want to put on it. But essentially, if machine builders are going to address these requirements for their end customers, they need to adopt digitalization technologies and digital twin technologies to meet these requirements. And with that, I'll pass it over to Scott.
Thanks, Colm. And what we're going to start talking about here is how do we get started with building this comprehensive digital twin that Colm talked about as being a machine builder to get these machines so we can get them tested. What you'll see here is we'll see a mock-up of the machine, and we'll talk a little more about some of the technology behind this running. It's actually the machine running. But next, if we look at how that machine's running, how do we tie it virtually to our automation? So what we have now is we have a virtual machine driven by virtual controllers. And how that digital twin comes to life then is next is when we take that digital automation and bring it into the physical world. And now this is the actual real machine running with the real hardware. And we're going to talk about how we bridge these two worlds together. But before we do that, let's take a look at what's really driving the use of this digital twin and digitalization for factory acceptance testing. Two of the industries that are really driving this right now are the automotive and the robotics industry, where they're demanding their machine builders to bring them the digital twin ahead of time so they can set it up in their digital factory, and not only that, to see if there's room for it, and to also digitally validate that it runs and it does perform the way it's expected to perform before they bring it into their shop to reduce their downtime for doing changeovers. Other industries we can see that are also adopting this digital twin technology are such things as the tire industry, electronics, food and beverage, aerospace, machine building, and on we go. We see a complete list of industries right here as Siemens we support across the globe. What you'll see here, though, is some of the boxes right now don't have that orange box around them. And what that means is if you're in one of those industries, you could be the leader in that industry, bringing that technology to those industries. But really, this whole digital twin virtual physical world and acceptance testing, what does that really lead to? It leads to what we call the explosion of complexity. And the common thread amongst all this is complexity. But some say that the answer is to limit or try to manage complexity. But we, as Siemens, believe that the true disruptors won't be trying to limit the complexity. We believe that if a business wants to move faster, if they want to lower their cost of development, lower their cost of production, all while responding to changing customer demands, while creating new business leaders, and out-innovate their competition and be the leaders, what they need to do is they need to take advantage of that complexity. And what does taking advantage of that complexity really entail? Next. In the complex world, what we'll see is sometimes people say, well, with enough data, the numbers speak for themselves. But that really implies an end of the science or the scientific methods we know and understand today. But some studies have shown that there are correlations of data just due to the sheer size of the data and looking for stuff that doesn't exist. For example, there's a study that's been done that looks at that there's a very high correlation between the number of people in the United States of America that have doctorate degrees in civil engineering and the per capita consumption of mozzarella cheese. So this correlation is degrees in cheese. It has really no sense. It makes no sense in any kind of context of business at all or in machine building or anything. It's just when you have so much data, sometimes you come up with these false positives. So what we want to do is have you be able to take advantage of that complexity through the most comprehensive digital twin, which is what we're going to spend quite a bit talking about today. Also, the personalized, adaptable, and modern interface of all of our tools along with open adaptable systems. And really, when we talk about a comprehensive digital twin, what we're talking about is the digital twin of the product, production, and performance. So what we're going to talk about today is how we move from left to right from a virtual traditional product into virtual production, into real production, to the real product. And you can see there's steps between the two where specifications and commissioning and testing go between those two. And really, what we get then is, what we do is we need to feed back that information. And within the Siemens world, we have what's called MindSphere, which is our IoT product and IIoT, to perform that feedback loop to get that continuous improvement throughout everything. But the majority of what we're going to talk about today is really in that center circle near the beginning next, is what we talk about the virtual production. And that's really the key what we're going to talk about. How do we virtually produce machines and virtually get them accepted out into your customers' businesses, so you can eliminate the need to have to stand out there on their shop floor and do quite a bit of that information. So next. So really, what does this kind of look like? And if we look at it here, here's a more detailed view of what we were talking about before in a little more detail. This is, if you remember this slide, we're going to come back to this one later. But this is really the virtual machine on the left. That's my kind of realm where we talked about I'm going to be playing the traditional designer, where I design the machine. I design how it gets put together, what it looks like, where we need to put the supports and stuff. And then we have on the right-hand side of the screen is how do we program that machine to run? What automation are we going to apply to it? What kind of signals are we going to do? How are we going to handle that information? And that's really where Colin's going to spend quite a bit of his area talking about today. And it's really these two get tied together where that virtual automation drives that virtual machine, not vice versa. So the automation engineers can be involved earlier in the process. And if we go next, how does that really look like in the process that machine builders traditionally use to get their machines out into the field? Today, what we mostly see is there's this distinct breakdown between the engineering of a machine and the manufacturing, stand-up, and testing of a machine. And today, it's pretty much a serial process that goes step by step by step. Whereas the sales force goes out into the field, they gather the requirements, they come back, they work with the concept engineering groups to quickly divvy up some new concepts and new ideas of how to build a machine and what it's supposed to do. Moves on to the traditional machine design, traditional 3D CAD machine design, parts, things, other things. From there, we start talking to the electrical group. They have to start running the wires to hook everything up. How are we going to power it? What else are we going to do? And then at the end, the automation group starts getting involved in how are we going to make this machine operate? What are we going to do when it has a fault? And start applying all this. Then that machine gets built out in manufacturing. Then that built machine gets taken out to the customer, stood up, and then we see if it works and we get them to buy off on it. What I'm going to do now is I'm going to turn it back over to my automation pal, Colin, and he's going to go through really how you can take this process. By using digital twin and digitalization, you can help eliminate a lot of time out of this process.
Thanks, Scott. And so from an automation standpoint, as you can see here, we're waiting for, say, the mechanical work to be done, and we'll develop as much of the code as possible. But until we have the real machine on the shop floor, it's difficult to really finalize your code and do all the iron out all the issues and alarm handling and bugs and so on. What we're talking about here today in the video that you saw earlier, where we just had the model running with the automation, is by using these tools, the mechanical improvements on the mechanical side, on the CAD side, to be able to simulate the mechanical components, as well as developing the interfaces with the automation software, where these two can work together. So the tools can complement each other. So virtual PLC, virtual HMI, working with a digital twin that's moving and simulating exactly how the real machine will behave, all of a sudden, we're able to do a lot more and move the automation person much earlier in the design cycle. So there's so much he can do. So by the time the real machine hits the floor, that actual commissioning time can be 10, 20, up to 25, 30% less, in some applications even more, depending what you're able to do. And the quality is much better. And so there's a lot of things as we go through the rest of the presentation. We're going to show the details. How can these two these profiles work together earlier to produce a much better machine, better commissioning, reducing the time, errors, and so on, and as we go through it. Now, we've, of course, been working with many customers in the U.S. about this topic over the last couple of years. And many times we're asked the question, okay, where's the cost justification to do something like this? And we have this simple, Six Sigma quality rule of 10 says that, you know, an unidentified error can increase by a factor of 10 from one value added to a value added level to the next. So the earlier the error is identified, the cheaper, of course, it's going to be for the organization. And we get this question, meaning, you know, there is going to be a time and a cost associated with developing the digital twin, but it's going to be down here at the early stage, and it will pay for itself as opposed if you have errors or issues or rework that has to be done much later on, especially out in the field where the real cost can get out of control. And if we take a look at some of the topics that some of the issues that people get into without doing proper digitalization or proper simulation of the machine, look how many there are time requirements. We talk to customers, it can be 4, 6, 8 weeks commissioning a machine depending on the complexity. If the customers are on site, if they're commissioning machine for a long time, there's a retention issue. We know customers who are looking at this technology purely from a retention standpoint. And then, of course, if you're using expensive materials to test on the machine, there's a scrappage issue. Especially your end customer does not want to have to scrap a lot of their expensive components just to test the machine. And if you have international travel involved, then the cost can really get out of control. So what we want to do today is we step down. You'll notice as we go through this presentation, we're going to go a level deeper and deeper to really highlight the value here. So there are 4 main use cases that we see. Customers taking advantage of. The first 2 are the obvious 2. Eliminating the errors, verifying the fault handling. From an automation standpoint, this topic clearly resonates that these are the things they don't get the time to really prove out on a real machine before they have to ship it. The sequencing of the operations, it may seem like an obvious one, but improved communications between the mechanical and the automation engineering group will absolutely give a better quality machine. But the next 2, these are ones that are, if you like, side benefits that you can use this technology with. Training. Again, if you have a virtual HMI, a virtual PLC, and a model moving like it's supposed to in the real world, then you can train an operator to have him use that interface and learn how to work with the machine before it's even built. And lastly then, this goes both for the machine builder and the end user. For the end user, there's the validation, and this is a big component of this virtual factory acceptance test. They want more than just a 2D print or a 3D print and a Word document describing how the machine is going to run. They want to use these tools that are originally designed, if you like, for improving the machine design and validate and sequencing, but for them, they get a much better understanding of how the machine will run. And then from the end, the machine builder, how do you promote or sell your machine? This is something that can be used. We see companies using these even in trade fairs for the promotion of their machine because their machines may be too big to bring to the market. So with that, let's go down and look at the tool set that Siemens has to literally empower machine builders to get ready for these virtual factory acceptance tests that we've seen, as Scott showed earlier, beginning in the automotive industry, and also we're seeing it in the tire industry, and it's coming into other industries. They're going to be end users, manufacturers are going to be looking for digital twins for virtual factory acceptance tests. So with that, go ahead, Scott.
Thanks, Colm. And what we're going to start talking about today is we're going to start talking a little bit about NX. And really, NX is really a single platform that contains all of the tools that are needed to break down the barriers between disciplines. NX allows all of your engineers, designers, and software people to collaborate and share information across the traditional barriers that exist today in single discipline solutions. But if we look at the entire circle of NX with the traditional mechanical design on top, then we have some electrical and process. The big area of focus today is next, as we look into that circle around the mechatronic design. How are we going to take our 3D traditional CAD data and be able to design it so we can use it for all this? Well, how do we do this? Some of it's through some of the 6 areas of NX that we talk about. NX is the world's most productive modeling environment because it models across all multiple disciplines to be able to get what you need in there. The next one is generative engineering. The next one is generative engineering. How can we take advantage of the power of the computer to help it solve and maybe do some simulation-based design in the context? The next one, industrialized additive manufacturing. From a perspective of Siemens, what we'd like to talk about isn't using additive manufacturing as a prototyping tool. We like to use it for production machinery, production parts today. Also electromechanical design, which is really at the heart of the electromechanical and mechatronic design. How can I bring all these disciplines together so they can all consume the data in the format they need and work in a collaborative environment to break down those traditional disciplines between multiple solutions? And then when you're doing all that, we talked about complexity before, how do I manage that design and how do I collaboratively do that? And finally, NX is built on a platform that not only includes a full set of design tools that we're talking about today, but a complete integrated simulation and manufacturing solution. So I can use one set of data across my entire engineering and manufacturing discipline, so I don't have to remaster data across other products. And if we go next, what we'll see here from mechatronic design is what we'll see here is the moving model of one of our machines. And the important part to know here, and we'll talk a little more how we hook this to the automation a little bit, is if we look at that box that's on the left, what that is not really a traditional, what we say is CAD modeling, but if you look closely at it, what it is, it's the definition of our machine from a physics standpoint. Where are the sensors? Where are the movements? How are we going to put this all together? Where do the signals go? What is the mass of these things and what's driving these parts to move? This is not just a kinematic simulation of the machine. This is a real physics-based simulation of how that machine will work, which is super important in machinery because a lot of times we have high-speed machinery that's really critical to that. We're not just doing, it works, it moves, but also accounting for all of the other physics. And with that, I'm going to turn it back over to my automation colleague who's going to take you how do I now take these 3D models and hook them up to the automation and a little bit into the physical, into the digital world.
Thanks, Scott. Now, from an automation standpoint, but even like from a mechanical standpoint as well, when we look at the simulation within a factory, we have to look at the different use cases for what we need to simulate. Is the use case the simulation of the PLC and HMIs, virtual PLC, virtual HMI? Much of that we can do today already for many years, actually. But what about if I need to interact the mechanical system with the automation, just like we showed earlier? Or if I have robots in the system, a single robot or multiple robots or a whole cell or a line or a plant. There are many different use cases where simulation and this idea of a virtual factory acceptance test can come into play. So one of the main things that we wanted to show you today was to give you a highlight of the tools that we have from the Siemens simulation product basket at every level, from the PLC, simulating the HMI, simulating the drives, being able to size components to make sure from a system level simulation everything's working together, having a CAD simulation of the actual machine running, or using robots to the whole robotic cell in conjunction with with virtual PLCs, or on the plant level, the highest level plant simulation. So I'm going to give just a quick overview of each one of these tools, and then we're going to dive specifically into our Mechatronics Concept Designer and our virtual PLC. But I want to begin with the AMASIM tool, what we use for system level simulation. So AMASIM, in conjunction with PLCSIM Advanced and virtual HMI, we can use the AMASIM tool to simulate how the components themselves will actually behave. So there is a series of equations behind the data set, behind each component that's on this machine, be it a valve, be it an electrical component, hydraulics. One of the really great things with AMASIM is that it's a multi-physics simulation tool. So thermal, hydraulics, fluids, electrical, mechanical, all can be simulated how the components will really behave. And then we can interface that with our virtual PLC and virtual HMI to really see are our motors, our valves, or whatever, are they sized correctly? So if that's what you need for a digital twin side for simulation, we have a tool for that. The Mechatronics Concept Designer is where we want to go a little bit deeper here, where we have the CAD visualization along with our virtual PLC and the drive simulation if need be. Process simulation is a tool that we use for the robotics. And again, This is robot agnostic. So KUKA, FANUC, Staubli, ABB, all of those vendors, those components can be brought into the process simulation tool to simulate end of arm reach, to welding and teach the path, everything around that. In addition, the components around the robots in the robot cell, they too can be simulated and connected to our virtual PLC, so we can simulate the complete cell and not just the behavior of the robots themselves. And then finally, we look at our plant simulation tool. Plant simulation, as the name implies, is really around for material handling simulation and the arrangement, the placement of the machines in a factory, working with AGVs, warehouses. So again, it can be standalone. It's got a lot of really great statistical tools. So this is, for throughput capacity. Is the line big enough to handle what's required? But we can connect that, like all the other tools, to a virtual PLC to verify its behavior. But let's go a little deeper now into the Mechatronics Concept Designer, along with our virtual PLC, PLCSIM Advanced. One of the key things about PLCSIM Advanced is the ability to simulate the complete automation program, but more importantly, it also has an API that allows us for high-speed synchronous communication to any of the modeling tools that we mentioned. The ability to simulate the entire automation program is one of the things that differentiates itself against many other competitors, if you like, or vendors in this industry, where there may be changes or modifications needed to the virtual PLC before you go to a real PLC. That's not the case with the PLCSIM Advanced. For all of the Siemens 1500 PLC family, we can simulate the entire PLC program, including the safety, and that's very important. The API allows for the high-speed synchronous communication with the modeling software, and if need be, we can simulate multiple instances if there are multiple PLCs needed to control the machine. So not only can we simulate, can we work with our own tools, but if there's a third-party application that needs to communicate to the PLCSIM Advanced tool, then we can use the API to send the signals back and forth. So a very handy tool. But in summary, using this API, that's one of the key things that differentiates the Siemens offering here against, say, other vendors in this industry, is this high-speed synchronous communication with our virtual PLC that is able to simulate the entire PLC program. So let's look at some of the use cases here. And then I want to, step by step, let's go through this. I'm going to pass it back to my mechanical colleague, Scott, to lead us through how exactly are we going to do this MCD model and connect in the automation.
Thanks, Colm. And before we get started on a little bit of details with it, what I want to do is I want to define two terms for everyone here today, right now, that how we define them. The first one we're going to talk about here is software in the loop. And what software in the loop means, what it really is, it's all virtual simulation. And we'll get to a little bit of detail in a second. And after we talk about software in the loop, we're going to talk about hardware in the loop. Is how do we eliminate the virtual controller and hook it up to a physical controller? So the general process now for being able to do this software in the loop validation of your products is most machine builders today start with 3D CAD models of your entire machine. And it does not matter where that machine comes from. It can come from any 3D CAD system, whether it be NX, SolidWorks, AutoCAD, CATIA, Creo, other ones. What you do is you bring it in, the mechanical model into the Mechatronics Concept Designer program, right? Next column. And then in the Mechatronics Concept Designer, we define some of those physics that we need to and do some of the things to set up the motions how we want. So now what we have is we have the model all ready to go. Well, at the same time, Colm's over there working in the TIA portal, totally integrated automation portal. What he's doing all his coding, all his automation work in conjunction while building the machine. And as we talk together, we work on the solution together. Then when the time comes, we put PLCSIM Advanced in between these two. And now what we have is we have the automation that's going to run on the shop floor, simulated, driving the simulated virtual model. And if we go to the next slide, this is that slide we started with earlier. That's what that slide was earlier on, which you can see here. As you can see, the Mechatronics Concept Designer on the left-hand side being driven through TIA Portal and PLCSIM Advanced, driving that model where we can monitor what's going on. We can make changes if we need to. How does this actually work? That's actually the virtual setup of it. And if you have a chance to ever come when we can all start getting back together down at the DMX Center in Chicago, we actually have this machine running digitally next to its physical one that's built to it too. In a second here, we'll get this movie kind of running. And what you can see here is you can see that we have the so that was the setup between the virtual and the physical and how the movies work. Now what we're going to talk about is how do we take and do this one step further down the way so people can actually feel and touch the controllers, kind of see what the output's going to be, not so much in a virtual world, but in the physical world. Again, we start with that same process from a mechanical end. We take our 3D CAD model, and next, we bring in the Mechatronics Concept Designer, how we did before. But now, instead of doing it virtually, what we're going to do is we're going to connect the real PLC hardware directly to that Mechatronics model and have it drive the virtual model. And to discuss a little bit more of that, I'm going to turn it back over to Calm, who's going to discuss kind of how that works through OPC and what some of the requirements are for that.
Well, thanks, Scott. So, of course, at some point we want to maybe connect the model to a real PLC just to make sure everything is running fine or connected to the real machine. We see that. And it's not just the Siemens PLCs, but with the OPC connectivity, we can connect to many other third-party controllers. And that being said, though, with the virtual PLCSIM Advanced, you know, we are able to do a tighter synchronization, a much faster control, and of course, we can do the safety all virtually. But it is possible to work with the third-party controllers if need be. Now I want to get into a little bit more detail. Exactly going to run some use cases here as where can we use this software. So collision detection is one of the things that from a design side, this is maybe a use case while you're building the machine. So in this little short video here, I'm running the virtual PLC in the background, and when I play the model and it tries to pick up the part, you can see it drops it. And that's because gravity, friction, and torque, there's a physics engine built into the Mechatronics Concept Designer. So in this use case here, I'm trying to verify how the parts are going to mate correctly, but I could also use this to verify if there's any interference. And of course, many other, say, CAD vendors may have some tools and ability to show parts moving, but the critical thing here is that the movements that you're seeing in here, they're being driven by real code running in a real PLC. And here we can highlight, if there is a collision, we can highlight the edge of the shapes, where we have the solid, where we have the rigid bodies defined, what's going to move, and so on. And so you can verify if there's an interference or how the parts will mate correctly, and then you can make the correction in the CAD model accordingly. So from a design side, that's a really helpful tool. Again, the automation driving the actual real the simulation that happens in the real machine. In this next video, I hope will address some questions many have on the webinar in regards to, well, how exactly do I connect the automation in with this modeling software? And the key here is all we're really doing is bringing in the signals from the PLC. In this case, I'm connecting to my virtual PLC or PLCSIM Advanced, and once I bring the PLC signals in, then I'm going to map them. So I have my external signals on the right-hand side from my PLC, and I have the internal signals on that the MCD uses to do the actual simulation. And I want to map those signals together. And that in itself really brings the mechanical and the automation engineer closer together, because the tag naming is a key aspect in making sure you have a successful project with this. And you can see here in this example, I have got a problem. It's crashing into the pole. So my sequence is wrong. So what should I do? So in this video then, in this application, just the automation engineer, I'm going to open up the block of code where I wrote that sequence. Now this block of code here, where we're using a scripting language, SCL for this example, but this could be ladder block programming, function block diagram, any of the IEC programming languages. It doesn't matter. So in my case statement here, I'm programming the simple steps. How exactly should this sequence move? And you can see I'm going back before I go up. And so my problem is here on step 4 and step 5 are backwards, because I need to move up before I move back in. So I'm just going to make a correction. I'm going to swap step 4 and step 5 on my case statement here. And the details of the code correction are irrelevant. The point is that I've found an error or a bug in my PLC code, and I've made the correction, and then I can, test that against the real model. So save, compile, download to the virtual PLC in the background. And the steps in doing that are identical to working with the real PLC. And once I monitor the code, I can come back on, and then I can turn on the part here, and you can see it picks up correctly. So that's an important part that I can really check. The next one here for me, I think, is critical in all of this is the error handling. So, and this is one of the key things for this virtual factory acceptance test that end users may look for. So I'm going to simulate an error in this model. I open up some of the part files associated. I've got a gripper here, and this gripper has a gripper open and a gripper closed sensor. And when I disable, I'm going to disable the gripper closed sensor. And when I do that and I run the model, you'll see that as the part comes out and it runs, it stays there as expected because it thinks the sensor is missing. So what should happen now? If I have a virtual HMI, then I can test the alarm, telling the operator exactly what he needs to do to go fix that. And so I can go through and test all of the sensors. And this could be something that an end user is going to want to know. What happens if this sensor fails? This is something that you can simulate for the user ahead of time and show him exactly. And more importantly, you can see there's a couple of other stations on here. If one station faults, how are the other parts of the machine going to recover? This is a key thing. Again, the end user, your manufacturer, is going to want to know how easy it is and show me how to get the machine back up and running if one part of the machine fails. And this is just another example showing the simulation, how we can, this could be an early design review with an end customer, a packaging example, where you see we come down, the parts, we're going to fill the package here, and then you'll see at the bottom of the screen is a sequence editor. And actually, this is a feature that the mechanical engineer can use before we make any connection to the automation to verify that the mechanical sequence is working correctly, to make sure design A versus design B, which is the better option. And then, of course, we would eliminate this then and connect the real signals coming from the virtual PLC or the real PLC at a later time. And you can see on this model here, we have the virtual sensor, this kind of pink rod here. When the box hits that virtual sensor, the part opens, and then it hits another virtual sensor in front, then to close it. So just another use case of how it works. This use case here, for me, is important to show the training aspect of it, because here we're showing a virtual HMI. This is a real machine we have in different digitalization location, and this is the real HMI that's operating this machine. So you can see when the gantry is running and the robot's picking and placing the parts, you can see the part positioning update on the screen. And so as an operator, I can learn how to interface, work with this HMI screen and get familiar with this machine before I even see it. This is something that absolutely manufacturers, it resonates that they can train their operators on using this application. And working with third-party controllers. So this is one thing we just wanted to show. Here's a third-party Rockwell PLC that's controlling the MCD here. So it's absolutely possible. This setup was done with a real PLC in the background via OPC connectivity. So we can do it for sure to make sure everyone's covered with whatever controller we're using. But make no mistake, with the Siemens virtual PLC or PLCSIM Advanced, it's going to be easier to set up, easier tag handling. We can do the safety, and then of course it's synchronized and much faster as well. So it is possible, and we can do it. Going again, just on the training scenario, this is very clear here where we have customers who want to do training kits where they will actually, you can put everything, simulate everything on the PC, but they may want to simulate with the real HMI and a push button station connected to a PC that's running the virtual model. And we see definitely machine builders are looking to do this so they can get a better business model. This is a training kit that they could potentially sell or help their end users train operators on their machine. So with that, I'm going to pass it back to Scott. So to talk about customers who's doing this now and what are the value that they're seeing.
Thanks, Colm. And we're going to start with one of the first customers here. We're going to start a company named Nextrum, based over in Europe and Austria. What they did is they've been building machines for 50 years. And pretty much what they said is, when we talk to them, they've been a long-time customer of our automation and engineering softwares. We've been working on our process over the last 50 years, and we can't make machines any faster than we're making today. That was until they embraced digitalization, because they were starting to see higher demands from their customers, from quality and quantitative and quicker speed. So what they did is they embraced digitalization, and they are now able to connect their digital twin for design and automation to simulate the machines before they build them, and they were able to reduce their overall development time for new machines by 50%. And this was after they said, well, we can't make machines any faster. So this is the story they have. Next one we're going to go to is a company called TronRoute next. And what we're going to do is we're going to see a little video. I'm going to kind of just point out some of the numbers here, but I want you to listen to what they have to say, not so much what Colm and I have to say. And they've been able to reduce their design phase by working together, like we talked about before, breaking down those barriers of multidisciplinary design. They've also the biggest thing that always gets me in this movie when I see it is not only that they shortened the commissioning phase on a complex machine that was multiple things running together, they had no physical crashes during the commissioning. And he'll talk about in the old days where they used to take stickers and little dots and put them all in the machines where they had interference while they were testing it. What that does, that eliminates rework of parts, engineering change orders, and sometimes if you're out at a customer site trying to get a machine up and running, having to have new parts delivered and manufactured overnight at great cost and expense to your company, while that machine's down and no one can be working. So with that, I'm going to turn it back over and we're going to go ahead and take a look at the movie.
The commissioning phase for us is very, very nerve-wracking. We are producing prototypes, mostly, and bringing the machine to life is very nerve-wracking.
The machine is packaging different kind of kilo bags, like potato chips, or it could be salad bags, into cases, which is already erected and fed into the machine from external. And it does so in an unprecedented speed. Virtual commissioning for us means that we can actually test a lot of things in a virtual environment before we need to build the hardware. We realized virtual commissioning with the NX tool and the Mechatronics concept designer and the PLCSIM Advanced together with the TI port. The main advantages we received on this machine with virtual commissioning is especially on the kinematics setup of this machine. Because of having two kinematic systems work in one shared space, we could test out the complete system in a virtual environment. And of course we had some virtual crashes, which saved us a lot of money.
The fundamental changes in this project is that we have brought together those design resources. The collaboration between software engineer, mechanical engineer and electrical engineer is more close. They work in parallel instead of step by step. So we have reduced the design phase by about 10% and the commissioning phase by around 20 to 25%. And that's the time on the shop floor is of essence for us, because if you can shorten that, you can produce more machines.
When you do the design, production, assembly, then the software guy starts to program. In this case, he actually came out with the software, pushed the button, and it worked. No collisions.
By playing with a virtual model, you can learn a lot. And doing that, it's fun. Doing on the physical machine, that's not fun, that's scary.
When we use MCD to test out these things in a virtual environment in the office, of course we reduce the risk of damaging the machine. And of course every damage to the machine is quite devastating to the commissioning time. So that's a big risk saver.
Earlier I had a little board on each machine where they put a dot for each collision they ended up with. And this could be converted into expensive bottles of brandy for the team to share. Today they only drink water because all the correlations are done digitally, not on the real life.
Siemens, ingenuity for life.
Okay, so thank you for showing that. I think before we go any further, we just wanted to just talk a few more things to wrap it up here. So hopefully you saw in that Tronert Engineering some of the key values that they saw, from definitely reducing that engineering time 20 to 25%. You know, that's real savings, and that will really, you know, the investment in this software pays for itself within two and a half projects, and we've worked it out with customers, and it's already paying for itself. So when we look at customers who are interested in doing this within the US here, we recognize that you may not always have the resources in-house to be able to develop one of these digital twins. And so we do have starter packages available, working with the Mechatronics concept designer, and whether your automation model is obviously, we hope, with the PLCSIM Advanced for high-speed synchronous control, or even with, if you need to work with a third-party controller, we can help you do both of those. And we have two starter packages. Beginning with the extended starter package, this allows us to we will do a 40 hours of digital twin development for the customer, including the MCD and PLCSIM Advanced. So we can come with a good starter packaging price for that. So essentially here, we're going to develop that digital twin for you. And you can work and learn, and we can mentor you in how to use the software as well, but we'll get you up and running to be able to use one of these tools quickly and implement the digital twin for a project. The basic starter package, basically, we're going to take advantage of the MCD player, and this is the cheapest option to get started. Really, it's a full service offering where we will develop the digital twin for you, and we can leave you with the MCD player, where you can play the model against your automation code, use it for training purposes, use it for marketing and sales promotion purposes. But if you're not necessarily, you still don't have the resources to maybe work with the MCD software yourself, you can use the Siemens resources to help you do that. So we have a basic starter package to get you going with the player version, or an extended starter package that we will give you, to get you 40 hours of full digital twin development to get you started on that, at least here in the continental US for that. So with that, I think we're coming up pretty close to our time here. I kind of wanted to maybe just pass it back over to Mark, if there were any questions there or any comments from Scott before we take some questions and wrap it up.
We can turn it over to Mark.
Very good. Thanks very much. You did have this last slide. Did you want to step through that?
It's really that's really just a summary of the final, our digital enterprise solution, digital twin product production and performance. But I think we're just a little bit tight for time here. I think we'll hit some of the questions if we can, because we had a lot of information on there so far.
Well, thanks very much to you both. And we do have time for questions. The audience may type questions for the presenters in the Ask a Question box on the screen, and we'll get to as many questions as time allows. Questions that we don't get to today will be posted online at controleng.com with the archive version of the webcast. Remember to download a certificate of completion or a copy of the presentation by using the Event Resources tab on the left side of your screen. And now on to the questions. So the first one is, what's the process to use non-NX data with the Mechatronics concept designer?
Hi, Scott. I'll take that one. Obviously, being from the mechanical side and the NX side, really, what the benefit of having, it's just as simple as bringing in the data from your existing 3D CAD software, and the NX tool has quite a few direct abilities to open directly the data from certain CAD softwares, right? We can directly open SolidWorks, Creo, TIA, and a couple others where you just say file open it up, bring it up. There's no need to do data translations between the systems. It will handle it automatically. Once it's in, you just apply some of the constraints you need in joints and motors, and then you just hook it up to your automation and go ahead and just run that way. And then if you need to make changes, you go back to your original authoring system, make changes to that data, and just bring that new component right in place of the old one. Everything stays tied together for the most part, and you just keep running it on as you need to make design changes. So one benefit is, if you do use NX though to design your data, is you do not have to do some of that extra work when you first bring it in, because when you design it in NX from a mechanical CAD perspective and bring it into Mechatronics Concept Designer, because it's all of our technology, we can just automatically absorb that information from the CAD model. You know, some of the assembly constraints of how the assembly is put together, which leads to how some of the motions derived and a few other things like that. So that's the answer to that question.
Great, thanks.
Any other questions out there, Mark?
You mentioned ability to use third-party devices. What are some of the differences between using MCD with, say, a Rockwell PLC versus a Siemens PLC?
Thanks, Mark. I mean, that's of course we get that all the time here in the U.S. of course, but I think well, there's a couple of key. While the Mechatronics Concept Designer and any of the simulation tools we showed, their Process Sim, Plant Sim, you know, they all will work with different third-party controllers using OPC UA. There are some limitations with that, and more importantly, there are differentiators from Siemens with the PLCSIM Advanced that we've included. So again, for all of our S7-1500 PLCs, the PLCSIM Advanced is an option package that will simulate all of them. And with that, one of the things it does is, you know, it allows for the high-speed synchronization. The API allows for that high-speed synchronization between the modeling software and the automation software. And that's very important so that, you know, your communication pipe between your modeling world and your automation world needs to be fast enough to actually be able to, your scan time of your PLC is going to be in milliseconds. You want to make sure that the modeling software is not missing signals, you know, the data handshake between them. That's really important. But I think one of the key things is the PLCSIM Advanced ability to simulate the complete program, and that including the safety, because it has the ability to allow the communication for the safety signals in the communication protocol that's required. So from the third-party controllers using OPC, you must have a physical PLC beside it. There are no virtual PLCs on the market now that can do what we're doing. It would all require what we refer to as a hardware in the loop. You would have to have a physical PLC, and while it's possible, definitely, how are you going to handle the safety and the high-speed synchronization? And you know, it's just overall, it's going to be an easier solution with the Siemens setup, but definitely possible, of course, with third-party controllers, as I showed in the video in the session. So.
All right, good. How reliable is this when talking about a machine that's semi-automatic?
For semi-automatic, I mean, I think not quite sure of the question there. I mean, the reliability, it really comes down to, if you like, the speed and performance between the virtual PLC and the model. And as long as you have a performant PC, I mean, yes, you will need a performant PC to drive the graphics. That is a requirement. But if you meet the minimum requirements for running the modeling software and you have a high-speed synchronous connection, then you should be as close to real time as possible. So whether it's automatic mode, semi-automatic mode, that shouldn't make any difference.
And time for one more question, and we'll get to the rest online. Who do we talk to about the packages?
Well, you can reach out to me or Scott, but I mean, the starter packages, that's part of something that I'm promoting in the US right now. So you can reach out to me from this webinar, any of the contacts, and I'll be happy to follow up. If anyone who's interested in getting started with a digital twin, we can help you with that.
And Colin, we're going to have a post-session survey too, where you can let us know your interest there too. If you really want us to contact you, you can just let us know that too if you don't want to just call them directly. We'll do
Yeah,
that
that-
Very good. And I just click back to the contact slide so that they know that's all in the presentation, so they can get a hold of you. Excellent. Well, thanks so much. I'd like to also extend special thanks to our speakers and our sponsor, Siemens, for today's event. Now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. On behalf of Control Engineering and Siemens, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.